Hello, everyone. Welcome to Basic Analysis discussion session with me. So this is week 9 of discussion sessions. Uh, so today I will be discussing a few problems on maxima minima, local maxima minima, global maxima minima, and we will try to solve uh, some problems on this. We will solve those questions today, and then we will see how uh, solving a few problems that we left in the last session. So in the last session, we So let's start with the formal introduction of myself. I'm Prerak from Gopal, and this is another live discussion that you are watching right now. Uh, Recording, you must be watching one of the recordings at this moment. So these recordings are available on my YouTube channel named Maths with Prerak. Okay, you can search this YouTube channel and you can find other recordings as well. Yeah. Okay, so let's discuss some questions now. So question number one. So in this question number one, we have a bounded variation function, and now we need to say which of the following statement is true. The first statement says that if f is a Riemann integrable function on the closed interval AB, then f is Riemann integrable on CB for all C that is contained inside AB. Okay, but not the converse. So let us first analyze this option A. So option A says that the function is that f is Riemann integrable on AB. Okay, this is given to us. We need to we need to prove that f is also Riemann integrable on C comma B for any C in A. Okay, so this is we need to prove. Okay. So we just use the definition of the Riemann integration. When do we say when a function is Riemann integrable, and then we will try to see how much far we can go ahead with that definition. Okay, how much uh, and then if we need anything else, we will try to impose those conditions as well. So let us just use the definition uh, for the given hypothesis. Okay. So since f is Riemann integrable function on the closed interval EB, so so for some epsilon greater than zero, for every epsilon greater than zero, there will exist a partition. There exists a partition P, let's say xi, where the of AB such that UPF minus LPF, this difference is smaller than epsilon. Okay, so this is given to us that UPF minus LPF is smaller than epsilon. Yeah. Now we want to show that for any C, if I choose in between the interval, uh, we will be able to find out a partition like this, so that things will uh, happens to be. true, so that for that partition, this criteria will be satisfied. Okay. So now the question is, we need to. So as I mentioned, question is to find out uh, a partition of CV. Okay, so question is to find out a partition of CV such that UPF, let's say that partition, call that partition to be Q, such that QF minus LQF is also smaller than epsilon, correct? So this is what we will now find for. So we need to find out such partition, and the idea to find out such partition is to use the given partition. Okay, fine. So how do we use this partition? That is the only uh, interesting. That's the only uh, part where you need to be attentive. Okay, so we know this fact that if I start the partition and if I have these conditions, okay, so any refinement of the partition will always be smaller than UPF. Okay, so for example, what I'm saying is, um, yeah, so what I'm saying is this. Uh, this is a fact uh, that let P prime be a refinement of P. Let's say P prime be a refinement of P, uh, then just a moment. Um, let's say P prime be a refinement of P, uh, then the sum, upper sum, with respect to P of F will be larger than the upper sum with respect to P of F. Okay. Similarly, and the lower sum with respect to P will be smaller than the lower sum with respect to P prime. So in other words, if you consider difference between UPF and LPF, if that sum, if the difference between UPF and LPF is smaller than epsilon, then for the refinement also it will be smaller. Okay, so this is the fact. And now if you want to recall what refinement is, refinement means whatever the point uh, are involved in partitioning your given set AB by a partition P should also be part of the partition given by P prime. Okay, you can add more points than whatever you are already having in P. Okay, but you can't remove any of the points from the given partition if you are considering the new partition to be the refinement of the previous. Okay, so we will use this fact in particular to prove this result. And how we will use that? Because just look at this interval that I'm going to draw now. So look at this interval. Think of this interval as AB. Okay, uh, this is, let's say, these are the, okay, so let's make it, since I have already said this is an interval, so let's think of, okay, so this is AB interval. Okay, and we already have a partition P of this AB. Now let's say, think there is a point C you have chosen. So C, which is sitting between A comma B. So this is a point C. Let's not make it in middle. Let's shift this point C towards A. So this is your point C, and you already have a partition of AB for which this criteria is already holding. Okay, so let's draw those points as well. So you are already having x n minus 1, some x n minus 2, so on and so forth. Let's say this point lies between some xj and xj, xj plus 1 and xj, and then it goes to x1. Okay, so this is the partition of the set that is already given to you. So since the C is an interval AB, so you can find out. So there will be So there is so this implies that C will belong to for some J. Okay, for some J varying from 1 0 to n. Okay. By introducing a new uh, partition point, which is C. Okay, so now you think of this new partition, which I'm going to write Q, or let's make it Q naught. Okay, now think of this partition, which I'm writing in red or in black right now, combination of both colors. Now think of this partition, uh, yeah, which is the previous partition P and union with the extra point C, where the C is in between X. Yeah. Okay, this is not every all point, but this C union with this C. Okay, so this partition will look like X naught, X1, Xj, then C comes in, then Xj plus 1, and up to Xn. Okay, so this will be the partitions that I'm looking into right. So this will be my Q naught. So this will be my Q naught. Okay, now given this Q naught, I want to yeah. So given this Q naught, uh, yeah, and now clearly this Q naught is a refinement of P prime. P, sorry. So let us write those facts as well. So clearly Q naught is a refinement of P. Okay. Uh, so so we already have this condition that U Q naught F, uh, which will be the summations of M, capital Mi, let's say Mi, I varying from 0 to n plus 1. Now you have shifted one point to each other because now you have n plus 1 points. Okay, so you have shifted your, so let's start with 1 to n plus 1. And the distance will be xi minus xi plus 1. And let's denote it because these reference points are different than the previous one. So we denote it by x1, xi prime. Okay, yeah. So ideally it should be written in the other way around. Correct. Yeah. So this will be your partition. And let's call this difference also m prime I, where let me uh, say what are all these symbols are. So mi prime is the supremum of fx when x is in between xi prime and xi plus 1 prime. Okay. Similarly, you define the minimum to be the infimum of fx with respect to the new partition. Okay. Similarly, now mi will be the supremums with respect to the older partition. Okay. So with these notations, let me write L Q naught as well, the lower sum varying from 1 to n, small mi xi plus 1 minus xi. Okay. Now, yeah. Now notice that this UQ naught F. Yeah. Now this UQ naught F is nothing but you write it like I going from 1 to j. Okay. So by m prime xi plus 1 minus xi prime, and then uh, what will be the jth? Uh, so j so jth will be from this to this point, and now you will move on this from this to this point, breaking this interval into two parts, and then the rest of the part plus uh, yeah, and now plus mi. Sorry, let's say it to be mj. Okay, so c minus xi, correct, and then there will be another term involving this to be cj, and then this needs to be uh, m prime falling to be m prime, and then m prime xi plus j minus c. Okay, and then the rest of the sum will be again mi prime xi minus xi plus 1 minus xi. uh, I is varying from, now it will start from uh, j plus 1 to n. Okay, so we have kind of break it. uh, yeah, so you have kind of broken it into two parts. Correct. Okay, now what do we want actually? So we only want to consider this much of the part because this is the CV interval. Okay, so we are only interested in this partition. We are not interested in the remaining partition. So up to C it doesn't matter. So I can further make it like this, that C minus xj. I can further involve it in this in this first summation. Okay, so the rest of the summation will be part of this and involving this into this summation. So basically, I'm breaking this upper sum into two parts. That's what I'm doing. Okay. Yeah. So let me write what we want to do is that, so let's say call this smaller partition of CP. So consider Q, which is nothing but uh, call them to be yi. Um, C being y naught, y1 up to yn being b. Okay, where these each yi is nothing but xi x j plus I. Okay, why? Because j plus I, because whatever is in the first place, so this j, it is now shifted by j many things. So it is so this is my y1 and it is nothing but j plus 1, correct? So so this is my, so in the new partition this will be y1 and this will be yn. That's what I'm doing. I'm defining this new partition, and what do we want to prove? We want to prove that uqs minus lqf is smaller than epsilon, correct? So now what is this UQF? UQF minus LQF is nothing but Uh, so now now consider that after this y1, after y1 to yn, everything is same. Okay, y1 to yn, the uh, points that I am having, those points are similar to the previous partition because it's just nothing but the refinement. It is similar to the previous partition. Correct? Yes. Yeah. So if I come back to this partition, so this whole thing is what is my Q not F. Correct. So this summation plus this is equal to, sorry, this will be QF. Correct. This is QF, and this is the remaining portion. Similarly, LQ naught I can also break into these two parts. Okay, so UQF is UQ naught F, or other way around, UQ naught F is equal to UQF plus the subsidiary part. This I varying from 1 to J, Mi xi plus 1 minus xi. Uh, Correct. Similarly, LQ naught. Okay. Yeah. Yes. So now this, yeah. Now clearly, if you write LQF minus LQF, okay, basically you're subtracting these two equations. So this will be smaller than. So in other words, what I'm saying is uh, this, sorry, this implies that is larger than QF is larger than this thing. Correct? These two equation imply these things. And now if you take the difference of these things, okay, so we can't say exactly because we don't know what these uh, mi primes are. Okay, so let's not go into that uh, part. But what we know for sure is that if I consider difference of these two things, okay, if I consider difference of UQ naught F and LQ naught F, okay, Q naught F, and difference of the right hand side, it will be smaller. This thing will be smaller than this because this difference of these two terms, which will be mi prime minus mi prime, this difference will always be positive. Okay, this difference will always be positive. So if you sum it up these things, so this sum from I to j will give us some positive quantity. calling it to be, let's say, k. Okay, so if you difference these two things, uh, so this will be equal to, this difference will be equal to plus some k. Okay, so if you just write, if you want to just write down the inequality in terms of uq naught f and uq f, so you just so this will be just plus something k, and if you remove this k, you will get this inequality, correct? And since this k can be zero also, depending on the choice of sorry, depending on the choice of the partition that you're taking, or the maximum minima, they might be equal also. So this equality sign also appears. Okay, and now since this thing is smaller than the thing, the right hand side difference is smaller than the UPF minus LPF, because it is because Q naught is nothing but a refinement of partition P. So this thing is smaller than the difference between UPF minus LPF, which is smaller than epsilon. Okay. So for a given epsilon, I have found out a partition Q such that the upper sum minus lower sum difference, upper sum minus lower sum is smaller than epsilon. Okay. So yeah, so this and further, if you try to understand the partition diameter also, the length of the interval in that partition, that is also smaller than the partition length given in P. Okay, so if you think of that the partition length was delta in this case, in P, which is the minimum of all the partitions, in subit of the, which is the minimum of the length of all the subintervals, correct? Xi plus 1 minus xi, I varying from 1 to n, correct? So, which is the difference, which is the smallest length. So, this delta will be smaller now. Okay. Why? Because you have further partition one of the, yeah. So, either it will be smaller or it will be equal to delta. It can't be larger than that, because we don't know that this xj minus xj plus 1 is the smallest subinterval which attains this delta. So it will be either delta or it will be smaller than that. So in this case, the q, so this also implies that length of q is also equal to or smaller than delta. Okay, so we have found out for given epsilon, for epsilon positive, there exists q of length smaller than or equal to delta of, there exists a partition q of CV with length such that UPF, sorry, UQF, correct? So this implies that F is uh, Riemann integrable on CV. And now since C was chosen arbitrarily, so for all C in AB. So what we have proved now, let's come back to the original statement. So we have proved the one side of the statement, that if F is Riemann integrable on AB, then F is Riemann integrable on CV for all C in AB, but not conversely. So it is also true conversely. We will let us show why it is true converse why converse is also true. So converse. So what is the converse first of all? So converse is, um, if R, sorry, if F is Riemann integrable for all C in AB, then F is Riemann integrable on AB. Okay, and the proof is pretty simple. It directly comes from the first statement because this is the stronger part. and this comes from this fact. If you take C to be equal to A, okay, then F is this thing. So this is the proof. Take C to be equal to this, then this F is a non-integer. Okay, this is the proof. So converse is also true. Okay, so that means the first statement is false. Now second statement says that F is Riemann integrable on CV for all C, then F is Riemann integrable on AB, but not the converse. So we have seen uh, that if F is Riemann integrable on AB, then it is also Riemann integrable on each point uh, that lies in between. Okay, so this is also false. F is Riemann integrable on AB if and only if F is Riemann integrable on CB for all C in AB. Okay, except and only if a statement. So that is also true. So this is true. But the limit as you approach uh, C, as you approach A plus uh, via C, basically you are approaching A plus via from the left hand side, from the right hand side. Then this integral, the limit of this integral may not exist. But this is not true. This limit also exists. Okay, and what is this limit? This limit is nothing but this limit is precisely um this limit is precisely the integral. Okay, so this limit is precisely the integral, and how do we see that? This I leave you to I leave it as an exercise, uh, and the proof is nothing but coming from this fact only that the UPF minus LPF their difference is smaller than epsilon. So what do we mean by uh, C going towards the this thing? That means I'm considering a different partition. So okay, the partition is changing of the interval. So this because of this limit, because of this the difference of the upper limit and the lower sum, upper sum and lower sum is smaller, is getting smaller for every epsilon. The limit will also exist. Okay, I leave this part to you guys to think. So this is also not true. So what is true is the D statement is true. Okay, now let's move on to discuss this question number two. In this question, again, it's again true and false type question. We have given two functions f and g on closed interval a comma b, which are Riemann integrable. Now the question is, uh, then the maximum fg and the minimum of fg are those functions also Riemann integrable? And the answer is yes. And it comes from the very basic fact that again the algebra of the functions. So the idea is to write maximum of fg as in terms of fg. So we write it as fx, yeah, fx plus gx divided by 2, okay, uh, plus gx minus fx, their absolute value divided by 2. Okay, so this is how you can rewrite maximal of fx. Similarly, you can rewrite minimum of fx in terms of fx and gx by taking the difference of these two quantities. Okay, and now we just apply best value, use the properties of integration. To prove that calling these functions to be hx and best probably capital Mx, small m. Okay, so I leave this part as an explain because this is direct summation of two integration Riemann integrable function is Riemann integrable. Okay, composition difference is also Riemann integrable, and you have composed it with the continuous function. Okay, so the composition in this way will also give us the Riemann integral. Riemann integrability results under this composition. So, and it is again then the sum of two Riemann integral functions. So, it is a Riemann integral function. So, there is nothing more to prove than just use the fact that you already know. So, this is a true statement. Now, let's move on to discuss question number 3. Okay, so before going to this, let me ask if there is any doubt. Okay, so now let's discuss uh, this question. Question number 3. So if a function on AB is Riemann Stieltjes integrable with respect to some monotonic increasing linear function, then it is also Riemann integrable. Okay. So we have given that this function AB, now this function f, which is Riemann Stieltjes integrable on AB with respect to some monotonic linearly increasing function. Okay. So we have f. So let f be Riemann integrable function R alpha to denote that it is Riemann Stieltjes integrable on AB, correct? Uh, where alpha x is a monotonically increasing linear function. Monotonically increasing linear function. Um, so that means it is of type ax plus b. Okay, but a has to be positive because the slope is always increasing. So a is increasing or it is 0. So it has to be a has to be positive or it has to be non-negative. Yeah, that's true. B is the intersection on the y-axis, so it doesn't matter. It can still be that intersecting also, but A can't go beyond. Um, it can be 0, but A can't be negative. Okay, that is correct. So with this condition given to us, now we need to prove that it is a Riemann integral function as well. So we need to show that f is a Riemann integrable function as well. Okay, so let us write not AB. Instead of AB, let's say write CD. CD, where C is positive. Okay, so again we will use the definition of Riemann still and try to find out how do we show that. So to show that f is Riemann integrable on AB, it is equivalent to show that for epsilon greater than 0, there exists a partition P such that UPF minus LPF is smaller than epsilon. Okay, now what is UPF and LPF? In this case, UPF and LPF will be Mi minus Mi, difference between xi plus 1 minus xi. Okay, and this summation goes from 1 to n. This is smaller than epsilon, where P is my xi, where P is A is equal to x naught, x1, so and so forth, xn being equal to B. This is my P. Mi is supremum of fx when x is in this interval. Similarly, mi is the infimum of fx when x is in this interval. Correct? So now this is what we need to prove. We need to find out such an interval of a. We need to find out such a partition of AB such that this thing will be smaller than epsilon. And what we have given, we have given that f is Riemann still just integrable. Okay, so what does this mean? This means that that for epsilon there is a partition P. Okay, there is a partition P with such that for hmm, such that UPF alpha minus LPF alpha is smaller than epsilon. Now, what is this UPF alpha and LPF alpha? UPF alpha is Mi alpha xi plus 1 minus alpha xi. Okay, minus Mi alpha xi plus 1 minus alpha xi, smaller than 0, smaller than epsilon. And this summation is going from 1 to n. Correct. Now, um, yeah. Now we just, what is alpha? Alpha is given to be Cx plus D type function. So let us use that fact. So if I just look at this difference, okay, which is alpha xi plus 1 minus alpha xi. If I look at this difference, it is equal to C times xi plus 1 minus xi. Correct? This will be this C times xi plus 1 minus xi. Okay. So if I replace this back into the equation, what will I get? I will get that mi minus small mi. I have clubbed those t. I have clubbed these two uh, things. I have taken this alpha xi plus 1 minus alpha xi out. Okay. So what will I get? C times xi plus 1 minus xi. Okay. Summation from 1 to n. This is being smaller than epsilon. Correct. Now this C is still problematic. How to deal with this C? Correct. So in order to deal with this C, uh, first we need to observe something. Observe this that observe this. Uh, if I can take this C out, whatever is remaining, this part is same as UPF minus
LPF. Correct? This part is same as UPF minus LPF. Okay. So, so the partition which is given by this Riemann Stieltjes integral, this partition is enough for me to prove that it is Riemann integral. But the only problem that I'm facing right now is this C. So how to get rid of this C? So we can get rid of this C by having some C over in this epsilon as well. Okay, suppose instead of epsilon, if I have C epsilon, then this C could have been removed. So, but can we do that? Can we consider C epsilon instead of epsilon? Yes, we can, because we have given that f is a Riemann still just integrable. That means that for given any epsilon, I can choose my epsilon whatever I want. So for given any epsilon, there exists a partition such that this calculation will follow. Okay, so instead of taking epsilon, I let me take C epsilon. Okay, C times epsilon. And what is this epsilon? Where this epsilon is coming from? This epsilon is coming from this epsilon, for which I want to find out a partition. So for this epsilon, I'm taking this C epsilon, and now for this C epsilon, there exists a partition because f is Riemann is still just integrable. Okay, so I have started with epsilon greater than 0 to prove that f is Riemann integrable, correct? So I use this epsilon. Now I have observed that if I just repeat this calculation, but I need to start with some C epsilon. So I take C epsilon. Okay, this C epsilon is again positive. Why it is positive? Because C is positive. That's where the importance of C being positive comes in the picture. Okay, so because C is positive, epsilon is positive. Positive of product of two positive numbers is again positive. Positive. So it is positive. Yeah. So it is positive. And now for this C epsilon, what will I do? Now for this C epsilon, I use the fact that f is Riemann Stieltjes integrable. Okay, so I will get a partition. Okay, satisfying these conditions. Okay, so I will use this. Yeah, so I will use this partition to for this epsilon to prove that it's Riemann integrable. Correct. So what I need to do? So I have started with C epsilon now. I just need to replace everything by C epsilon. I just now need to remove. Uh, I just now need to replace every epsilon by C epsilon. Okay, so C epsilon appears over here and appear here as well. Now you can this is C epsilon. Now you can cancel out the C by C. So what will you get? You will get as a result that it is PF epsilon minus LPF smaller than epsilon. Okay, and now again, because this P, now there is a partition with this, such that this partition number one, this radius of the partition is smaller than delta, correct? And number two is this thing happens. So again in this case also, what for epsilon greater than 0, we have find out a partition P, which is a equal to x naught, so and so forth, x n equal to b, such that number one, that the length of the partition is equal to delta. Okay, and the second point is this thing, correct? So yeah, and this first fact also comes from the Riemann-Stieltjes integral part, and the second part also we have proved that it also comes from the Riemann-Stieltjes integral part by using Riemann-Stieltjes for C epsilon instead of epsilon. Okay, so this uh, implies, this is equivalent to say that f is Riemann integrable on AV. This completes the proof. Okay, now let's go back to this question. So in this question, it was again true and false type question. So if a function is Riemann-Stieltjes integrable with respect to some monotonically increasing linear function, then it is also Riemann equivalent. So that means this statement is true. Okay. Any question? Okay, now let's move on to discuss these local minima, global minima questions. Okay, now let's move on to this question number 4. Um, so in this question number 4, we have given a function um, in two variables, a real valued function in two variables, okay, which is defined to be as follows. Now, uh, yeah, again we need to pick which one is true. Okay, so first option says that this f has exactly 1 point of local minimum and 1 point of global minimum. Second point says that f has more than 1 point of local minimum and exactly 1 point of global minimum. Third point says that f has exactly 1 point of local minimum, no point of global minimum. Fourth point says that f has more than 1 point of local minimum and no point of global minimum. Okay. So let us recall. So whatever, if it is a one variable function, let us just bring down. Let us just recall first what is one variable case, equivalent case in one variable. So whenever we have one variable function, so we say that. So we can draw the graph of one variable functions. Okay. So the graph may look like this. Okay, or it may look like, or it may look like. Okay, so these are the ways it may appear. Okay, a graph may appear. Correct. So when do we say that it has a local minima or a maxima or a global minima or a global maxima? Uh, so first of all, the first thing that we check is for that whether does that function have any critical point or not. And how do we check that whether it has a critical point or not? We just look for a point where the slope is 0. Okay. So what is the slope of the graph? It is the straight line that passes through that point. Okay. So it is a straight line that passes through a point and touching the graph tangentially. Okay, tangentially means it is touching. It is not uh, intersecting through it. Okay. So these will be the so these will be the slopes, and the slope of this straight line is called the slope at that point. And how do you how do you get this? How do you calculate this slope? It is calculated by the df by dx. Okay, where f is the, let's say if this is the graph of some function f, one variable, then the slope will be calculated by this point by evaluating this at, let's say this is at x naught. So this is how do you calculate. So when do we say for local minimum and maximum, we can see that the slope is 0. Similarly, here also when where it is local minimum, it is 0, and it is also 0 at these 2 points. Okay, so these are all indications of the local minima. So in the first figure, the point y is local maxima. Second figure, point x is local, or you may say global maxima, because global minima, because it is graph is not coming back, seems to be like it's not coming back. In the third point, it is x1 and x2 are respectively local maxima and minima. Correct. Now, how do we get these points? We get these points by just solving this equation, df by dx equal to 0. Okay. So whatever function, one variable function you are having, you differentiate it with respect to x, and you evaluate it equal to 0. So you will get some value in terms of x. It will solve in terms of x. So you will get some value x, and now this value x will tell you that at that point function attains minima or maxima. Correct. Okay. Similarly, in two dimension, when you have two variable function, real valued function of two variables, the similar procedure can be applied. So to find out the local minima or maxima, we again go for we again check for, yeah. So we again check for uh, df equal to dx equal, sorry, the partial derivatives, because we have two variable function. So this equal to 0 and this equal to 0. So now we have two, because we need to find out 2 points, because we need to find out two variables, we need to solve for two variables, so we need two equations. We get two equations, but this is the first equation and this is the second equation. Okay, so that's what we will do. So if a function attains any minima or a maxima at any point x naught comma y naught, then at that point the partial differential with respect to x and y must be equal to 0. So in other words, if you want to find out that at what point function attains maxima or minima, you just need to solve these two equations. Okay. Suppose if these equation doesn't have any solution, that means the function doesn't attain any maxima or minima. Okay. And if these equations does have any solution, so what are those solutions? Those solutions will represent the point at which function attains maxima or minima. Okay. So yeah, so this question uh, completely depends on the solution of these two equations. So in order to find out that this function has exactly one minima or local minima and global minima, we just need to solve these equations. Okay. So what is our function? So function fx, function fx is x square plus y square minus 2x, x square plus y square minus 2x, 6y plus 40, minus 6 plus 6. Correct. So this is correct. Okay. So this is f of xy we have. Yeah. So now first equation is the partial differential of f with respect to x, and the second is partial differential of x with respect to y. So if you differentiate with respect to x, you get 2x plus 0 minus 2 minus 0 plus 0, which is 2x minus 2. The second equation you will get 2y, 0 plus 2y minus 0 minus 6 plus 0. So it will be 2y minus 6. Now evaluate both of the equations, df. If you evaluate a df by dx equal to 0, you will get x equal to 1. Similarly, if you evaluate partial differential of y with respect to partial differential of f with respect to y equal to 0, you will get y is equal to 3. So you get only 1 point, 1 comma 3. Okay, so this is the only point that you have got. So this point is a critical point of fxy. Okay, so whatever behavior, whatever, if it attains a maxima or a minima, this is the only point that it attains on. Okay, now this question is easy in the sense that because it only talks about the minima part. So we have seen that it has exactly one critical point, and at that critical point only it will either attain minima or a maxima. Okay, So now if I come back to the question, to the options, so the first option that it takes the if I come back to the options, so the first option says that f has exactly 1 point of local minima and 1 point of global minima. So it says that exactly 1 point. Okay. F B option says that more than 1 point. C option says that exactly 1 point of local minima and no point of global minima. Correct. And the third D part says that more than 1 point of local minima, no point of global minima. But if there is only 1 point of local minima, then it will also be the global minima. Correct. Because there is no point. Okay. Because if suppose if there is a global minima point. Okay. If suppose there is a global minima, so it has to be first of all a local minima. Okay. Because uh, correct. So whatever is the local minima, if there is exactly one local minima, then it has to be the global minima. Because uh, if it is not uh, global minima, so that means there are other points which are smaller than this point. Okay, correct. So now the answer is that if there is exactly 1 point of if there is exactly one critical point, then it has to be local minima as well and the global minima as well. Because if there is a global minima, then it will also satisfy those two equations, correct? And the solution will give us the critical point. Similarly, local minima also we need to check for those conditions only. And since there is only one critical point, so it has to be a local minima as well as the global minima. Okay, so that's why this answer is correct. More than 1 point is not an option because we are only getting 1 point out of solving those equations, satisfying those equations. So that's all. Okay, so this completes this question number 4. Any question in that? Okay, so no question. Then let's move on to discuss question number 5. In this question, you need to prove that the origin is a saddle point of a function f. Function is given to be x to the power 4 plus y to the power 4 minus 4xy plus 1. So let us recall when do we have a saddle point. Saddle point is like a figure of this type. Okay, so this I hope my drawing is convincible to you. Yeah. So what is this point? This point is a saddle point because if you travel along this red curve, let's call it to be A. If you travel along this curve, this point attains a maxima. If you travel along this curve B, then it attains the minima. Okay, so it is a saddle point behavior. Yeah, so that's example of saddle point. Now we have given a function, and how do we check that whether a function whether a point is a saddle point or not? So first of all, it needs to be a critical point. Okay, so first of all, it needs to be a critical point. And the second thing, we go for the second derivative test. Okay, so basically we find out the discriminant um, of f, which is nothing but the determinant of this function uh, fx. Okay, if this discriminant turns out to be negative, then we say that it is a saddle point. Okay, so let's solve this each uh, step by step. So in the first point, we have function f x y, which is equal to x to the power 4 plus y to the power 4. Now, to find out the partial derivative with respect to x, we first differentiate it with respect to x. So we get this 4y plus 0. Similarly, if you differentiate with f with respect to y, then you will get 0 plus 4y cube minus 4x plus 0. Now evaluate each to 0. You will get 4, basically you will get x cube minus x cube equal to y, equation A. Um, and you will get, by evaluating this to 0, you will get y cube equal to A as equation B. Okay, so now you want to find out the solution of which solving these two equations. So yeah, so by A and B, uh, we have y cube is equal to x. Okay, which implies that now y is x cube, so this, which implies that x to the power 6 is equal to x, sorry, x to the power 9 is equal to x. So x times x to the power x, 8 minus 1 is equal to 0, which is x is equal to 0, or x to the power 8 minus 1 is equal to 0. So uh, so x can be plus minus 1 as well. Okay, now for x equal to 0, you will get y equal to 0. For x equal to plus 1, you get y equal to plus 1. For x equal to minus 1, you get y equal to um, minus 1. Correct? So this 0 comma 0, which is origin, is a critical point of fxy. So now let's come back to the question. The question, it was given that the origin is the saddle point of f. So we have first thing is check out that it is a critical point. Okay. So it is a critical point. Now we need to check for the discriminant of other function, which is this quantity. So it is a critical point. Now let's see. Now what is fx? So we already know that fx is equal to, yeah, fx is 4x cube minus 4y, and fy is 4y cube minus 4x, correct? So fx x is equal to 12x square minus 4, sorry, this will be 0, 0, and fyy is equal to 12y square minus 0, and fxy will be 0 minus 4, and fyx will be 0 minus 4. So you get, so the determinant of this matrix 12x square 12y square minus 4 will be, at origin we need to check only. So if you check at origin, it will be now what is this? This is 0 minus 4 times minus 4, which is 16. So it is going to be minus 16, which is 0, which is smaller than 0. So the discriminant turns out to be negative. Okay, so hence 0 comma 0 is a saddle point of f. Okay, the second condition is that discriminant needs to be uh, negative, which it turns out to be. So first of all, it is a critical point, origin is a critical point. Second is that the origin is the saddle point of f. Okay, so this completes this question number 5. Now let's move on to discuss question number 6. Now question number 6 is a double integrable, is a function, is a the question of double integration. So let us see how do we solve this question. So we need to find out the double integration of the function fx, um, double integration of the function fx, which is x minus 3y square over the domain 0 comma 2 times 1 comma 2 is equal to what? Okay, so this interval is running over y and this interval is running over x. Yeah. Or maybe vice versa. This is running over x, this is running over y. Yeah. So we so this domain is nothing but as rectangle. Okay, so if you try to draw this domain, so it is 0 comma 2. Okay, so it is 0 comma 2 times this, so it is basically this domain. Yeah, so this will be the domain that we are looking into right now. So this is our D. Okay, um, Yeah. So this domain integral of fx by with respect to dx first and then dy. Now what is this integral? So d is 0 comma 2 times 1 comma 2. Fx is x minus 3y square dx dy. Okay. So if in some sense we can, if we can replace, if we can interchange the integrations, okay, uh, basically if I will be able to first differentiate this thing with respect to fx by dx with respect to dx with the limit applied, and then with respect to dy, then it will be very easy for me to solve this integral. So can I do this? So in particular, what I'm saying is this integral, when will this integral be equal to this integral or this integral? Okay. So this is a theorem which is called Fubini's theorem, which allow us to do this. And what is the hypothesis of Fubini's theorem? Hypothesis of Fubini's theorem is that the partial derivative needs to be continuous. So do we have this in this case? Yes, we have that in this case. Continuous. So these are continuous partial differential function. So f is a very nice function, and we can apply Fubini's theorem. In particular, we can interchange the uh, integration to get the desirable double integral function. So so this fact is important for us because this ease our life to solve this integral. So we just need to treat the integral as a integration of one variable, and at a time we only need to treat integration with respect to one variable, and yeah, solve the double integral. Okay, so applying the Fubini's theorem, so we have first a limit ab is 0 comma 2, and then it is 1 comma 2. Function is x minus 3y square dx. First we will integrate with respect to dx, and then we will integrate with respect to dy. So this is 1 comma 2. Now if I sorry, I meant integration. So if I integrate with respect to x first, what we will get is x square by 2, correct, minus 3 y square, it will remain as it is, times x. We apply the limit 0 comma 2 dy. Now what happens if I apply the limit? We will get 4 by 2. 4 by 2 will be 2 minus 3y square as it is, times 2, it will be 6 now, and if I apply 0, I will get 0. So we don't apply that. Now we integrate with respect to y. So we will get 2y square by 2 minus 6y cube by 2, limit 1 to 2, correct? So this cancels out thrice, this cancels out this thing. We will get y square minus 3y cube 1 to 2. So if you apply 2, so it will be 4 minus 3 times 2 cube minus 1 square minus 3 1 cube. What will be this? 4 minus 2 to the power 3 is 8. 8 times 3 is 24. Okay, minus 1 minus 3. So it will be 20 minus 20, and it will be uh, plus 2. So it will be 18 minus of 18. So do we have 18 in our? It is minus 12. Okay, so I must have messed up with the calculation. Okay, but you guys understand the overall picture, so you can repeat the computation, and you will get the exactly same result. So I might have taken the limit wrong. So you may try by taking limit x from 1 to 2, and uh, basically I might have taken the wrong domain. Okay, so you might take a domain to be this way, where 1, so you may take this domain where this is 1 2 in the x-axis you are taking, and 0 comma 2 in the y-axis you are taking. So um, yeah, so it will be like this domain. Okay, so try solving on this domain. I think this will give you the answer. Okay, yeah, but the idea is same. Oh, okay, so yeah, I have made mistake over here. I'm sorry. Yeah, so mistake is that it is 2y, so it will be just 2 times y, 1 to 2, and then it will be uh, yeah, it will be 6 by 3 y cube, because it is integration of yn is yn plus 1 divided by n plus 1. Okay, so yeah, so it will be then 1 to 2. So that's why this computation is wrong. I have taken the correct domain, but the computation was wrong. So this is 2 minus, this will be 8 minus 1, 7, 7 times 2. So this will be 2, and then 2 times 7, it will be minus 14. Minus 14 plus 2 is equal to minus 12. Yeah, so that's why. So this domain is not correct. Yeah, so this is not correct. I've taken the correct domain, and the answer is also correct. So the answer of this question is minus 12. Okay, minus 12. Yeah. So now let's move on to discuss question number 7. So in this question, again we need to find out the double integral of a function fxy, which is y times sine xy. Okay, over the domain 1 comma 2 times 0 comma pi. Now, yeah, again we will use a similar method to solve this integral, double integration. We will apply Fubini's theorem to see. Yeah, again, if you try to calculate the partial differentials of this, it will turns out to be continuous. So you can apply the Fubini's theorem. So just for a check, let's do that. So it is cos xy, y times cos xy, which is y square times cos xy, and sine y, sorry, fy, which is the partial differential of f with respect to y, it will be sine xy plus uh, cos xy xy. Okay, so it is again continuous. This is also a continuous function. This is also a continuous function. So we can apply the Fumni's theorem. Fumni's theorem is applicable. So in other words, in order to find out the integration of fxy dx dy over this domain D, I'm calling this domain D, okay, which is again a rectangle. This will be same as uh, finding this integral over with respect to x, and then finding integral with respect to y. So what is my fx? So my fx is 0 comma pi. So this is the limit of y, this is the limit of x, correct? So in x coordinate, I am moving from 1 to 2, and in the y coordinate, I am moving from 0 to pi. So in particular, this product will give me a rectangle in xy plane. So that's what I'm writing, the limits over here. And the function is nothing but y times sine xy, yeah, dx dy. Applying Fumni's theorem, I will get uh, y sine xy dx and then dy, which is 0 to pi. Okay, so this part, if I if I integrate this part, I just need to integrate with respect to x. Okay, so y will behave like a constant in this part. Okay, so I will just keep the y fix 0 to pi. Okay, and now you can also think, also you need to see that this y c is multiplied by a constant. Okay, so you need to perform some kind of change of variable in this case. So think of xy as some t. So dt will be y times dx. So yeah, now y times dx will become dt, and this will also affect the limits as well. So so limits will be from y to 2y, correct, of sine t dt. Okay, so after doing this, you will get cos t minus cos t y from 2y. Okay, 0 to pi dy, which is nothing but integration cos y minus cos 2y dy. So now this is a single variable integration. We all know how to do this. So now calculate this integration, 0 to pi cos y minus cos 2y dy. Okay. Now what is cos y? Integration of cos y. Integration of cos y is sine y. Okay. Apply the limit from 0 to pi minus what is the integration of cos 2y. Again, you perform a change of variable. Let's say 2y is equal to some p. So 2 times dy is equal to dp. Now since 2 is not here, so you can rewrite it as dp by 2. Okay. So you can replace dy by dp by 2. Okay. Um, so how, and the limit will also change. So limit will change from, so lower limit will be 0. Okay. But the upper limit will be pi by 2, because y is equal to 2, y is equal to py, sorry, it will be 2 pi, correct, because pi is pi, sorry, y is pi, so p will be 2 pi. Okay, so basically we are calculating this integral now, which is cos p dp. Okay, so sine y from 0 to pi, it will be equal to sine pi is equal to 0. Sine 0 is also 0. So this first part will be 0. Now what about the second part? Second part, if you integrate, you will get cos p, it will be sine p. Limit will be from 0 to 2 pi. Again psi p 0 to 2 pi, it is 0. So 0 minus 0 will give you 0. So this integration will be 0. So if I go back to this question, so answer C is correct. Okay. Um, yeah. Any question in this? If you have any question, you can unmute yourself and ask. Uh, okay, no question. Then let's move ahead to discuss this question number 8. So in this question number 8, we have given a function f of two real variables, a real valued function on two real variables, which is defined to be x times y square. Okay, for all x, y in R2, and you have given a region D, which region D of points x, y in R2, such that x coordinate is either equal to 0 or greater than 0, y coordinate is either equal to 0 or greater than 0, and x, y satisfy this inequality, which is x square plus y square is smaller than equal to 3. So this says that it is part of a disk of radius 3. This part says that it is part of the disk of radius 3. These two part, these two inequality, first two inequality says that it is part of the first quadrant. Okay, first two inequality says that it is part of the first quadrant. Second inequality says that it is part of a disk of radius 3. Okay, so now you need to uh, say you need to find out the maximum and the minimum value of function f in this region D. Now there is one thing you can just by looking you can notice the minimum value without thinking, without doing anything technical. So if you try to draw this quadrant, the domain, the region that is given. So if you draw this region, it is turns out to be this. Uh, okay, so it turns out to be this type of region of radius given to be 3. And more particularly, you are only looking in the first quadrant because x coordinate and y coordinate are also positive. So you are looking in this quadrant. Okay, so you are looking in this coordinate as well, and your function is of type x times y square. Okay, your function is x square, x times y square. Just a moment. Yeah. So your function is uh, what is your function? Your function is x times y square. So your function x times y square. Now clearly this function will always be positive or 0. Okay, it can't be negative because it is lying in the first quadrant. So xy lying in the first quadrant, so x and y always takes positive value. Product of two positive value is always positive. Okay, so this will always be positive. So x y square will always be positive if x and y both are positive, correct? And x y square will be 0 if and only if x and y both are equal to 0. Oh, basically either of them is equal to 0, either of xy equal to 0. ठीक है. Yeah. So in other words, this function will always be positive, either positive or equal to 0. So the minimum value, minimum value of fx will be 0. It can't go negative. It will always be 0. So this part is done. So minimum is always 0. So that means option A and option C are the contender for the so option B and D can be eliminated. So these are two options can be eliminated. Okay. Now let's understand the maximum part. Okay. Yeah. So in order to understand the maximum part, uh, you we need to observe one more thing. The one more thing that we need to notice here is that the maximum can only be attained on the boundary of the disk. Okay, which is the blue line, the blue arc that I have drawn. So okay, so notice that maximum of f can only attained on boundary of the region. Okay, why? Because uh, on the boundary only xy attains the maximum value. Okay, so yeah, so given any point inside the interior D, okay, you cannot find out a pair. Uh, okay, so for given any pair xy in the interior of the bound in the interior of the disk, you can always find out a point on the boundary which attains a bigger value than the point, bigger than the value that is in the interior. Okay, for example, if you think of this point, then this point corresponding to this point and this point, if you look at the boundaries value at these 2 points, these will be larger than this whatever value attained at this point, because at this point the x value will be larger with keeping the y value same, and at this point the y value will be larger keeping the x value same. Okay, so given any point you can always find out a point, given any point in the interior you can always find out a point on the boundary which attains the larger value than the point on that compared to that point on the in the interior. And this is strictly because of the fact that we are looking in a disk. Okay, so now we so for maximum we only need to understand the function on the boundary. Okay, so now let us reduce the function for the boundary case. So what do we mean by that? Because on boundary, uh, so boundary is okay. This is the boundary. Okay, so a set of all points xy such that x square plus y square is equal to 3. So on this boundary, xy satisfies this equality only. Correct? Yeah. So now from this equality, which is the circle, okay, and one more thing, that x is positive, y is positive, that is also needed. So we are basically looking at a arc of the circle. So from this we can write my x as the in terms of y, correct, 3 minus y square root of this, and why positive square root only, because x is always positive, x can't be negative, so that's why I'm taking the positive square root only. or in other words, I can rewrite y square as 3 minus x square. Why y square? Because my function has y square term in it. So I will just directly replace y square with this term. So after replacing, I can make my function xy on the boundary as a function of x, which will look like 3x minus x cube. Correct? Okay. So now on the boundary, my function is like a one variable function. Okay, it is no more a two variable function, it is a one variable function. And now for a one variable function, do we know any method to find out a maximum value? Yes, we do. And that is, so now my question has become, we want to find out maximum value of fx, which is 3x minus x cube. We want to find out the maximum value of fx. Correct. Okay. For x positive or equal to 0. So how do we do that? So first of all, function will attain maximum value. So in other words, we want to find out the maxima and the minima type thing. Okay. So for example, maxima function will attain when the graph of the function will be when the slope will be 0. In other words, df by dx needs to be 0. Okay, at x naught. So then this will correspond to the critical point, and then once you get the critical point, so you just need to check that two differential. You need to apply the second derivative test, which is d square by dx square at x naught. If it is turns out to be negative, then it is maximum. Okay, and then you calculate this point. Uh, then you evaluate f at that point. Okay, so we will do this step by step. So first let us differentiate my function fx with respect to x. What we will get? So df with respect to x, what will we get is 3 minus 3x square. Sorry, 3 minus 3x square. Okay. Now in order to find out point x naught, the critical point, you need to evaluate this partial derivative. This uh, single derivative of f at 0. So if you do that, you will get that x square is equal to 1. Correct? Which will implies that x square is equal to 1, which will imply that x is either equal to plus minus 1. But we are only looking into x being greater than or equal to 0. So we consider, so we only take x equal to plus 1 point. Okay. So this is our critical point. This is our x naught. Okay. Now we find out the second derivative of this point. Now what is the second derivative of, first of all, what is the second derivative of this function? So first derivative is 3 minus 3x square. So you differentiate it again, dy dx of 3 minus 3x square. What will get? 0 minus 6x. Okay. Now you evaluate your second derivative at x naught, which is 1. What will you get? 0 minus 6, which is, sorry, you will get this minus 6x, you will get minus 6, which is negative. So f attains a maximum now. What is the value of f in which this is in which you are interested? Correct? So now this value fx naught is 3x naught minus x naught cube. which is 3 minus 1, which is 2. So the maximum is 2. So maximum is 2. Maximum of f is 2. So minimum of f was 0, maximum of f is 2. So now let's go back to the question. So in the A option, we have 2 as a maximum, 0 as a minimum. In the C option, we have 3 as a maximum and 0 is a minimum. So obviously, option A is correct. So option C is also wrong. Okay. Any question in this? Any questions? No questions? Okay, good. Um, okay, I leave this question number 10 for you guys as an exercise. I will tell you how to solve this. So you need to find out the critical points of function f, and you have given a function. Okay, so what are the critical points? So critical point x naught of f if the partial differential okay, so since it is a two variable function, okay, this has to be 0. So this is the definition of a critical point. Okay, so in order to find out a critical point, you need to first solve these two equations. Okay, number one, equation number 1, equation number 2. So solving 1 and 2, solving 1 and 2 will give you uh, the critical point. Critical points x naught comma y naught. Okay, why I'm writing points? Because the solution may be more than one. Solution point may be more than one. Okay, satisfying these two equations 1 and 2. Okay, now in this case, what do you need to do? Just you need to find out the first partial derivative with respect to x. You need to find out partial derivative with respect to y, and then you need to solve the equation. So I will do up to some point that uh, so partial derivative of f with respect to x is where the function is x times y times e to the power minus x square plus y square. Okay, xy e to the power x square minus y square. Okay, so it is again you need to apply product rule over here, product rule of differential. So first we differentiate this part and then the second part is this. So y will come out e to the power minus x square minus y square remain as it is, and plus now xy stays as it is. We differentiate the second part, so minus 2x comes up, and then e to the power minus x square minus y square remain as it is. Okay, so now you can take this common. What will you get? You will get 2y x square. ठीक है. So you can even take y common. What will you get? Minus 1 minus 2 x square. Correct. Similarly, df by dou x will be x times e to the power minus x square y square 1 minus 2y square. Okay. Now you need to solve these two equations. So e to the power minus x square y square 1 minus 2x square is equal to 0, number 1. Second equation is x e to the power of x square minus y square 1 minus 2y square is equal to 0, number 2. Now, जो, now this function, exponential function, is always positive. Okay, what do we mean by that? That e to the power minus x square minus y square is always positive for all x, y in R2. Okay, so it can't be negative. So these two equations will lead to you two different set of new equations, which is this first one. Second one is x times 1 minus 2y square equal to 0. Okay, now you solve these two equations. So what are the equations that you need to solve? First one is this. Second one is, now from the first one, you can say that y is either equal to 0 or 1 minus 2x square is equal to 0. So if you solve this, you will get a 1 over square 1 over 2. That means plus minus 1 of 1 over square root of 2. Correct? So these two cases breaks into when y is equal to 0. So if you replace this into the second equation, what will you get? You will get x equal to 0. So this will be your one solution. Okay. Now when x is equal to plus minus half, you plug this into equation number 2. Okay. Plug this into equation number 2. What will you get? You will get 1 over square root of 2 plus minus uh, okay, and then y will also be equal to plus minus square root of 2 in that case. You can just directly multiply it to 0, and now this will be one thing. Okay, and when you assume that y is in the second equation, when you assume that x is equal to 0, sorry, x equal to non-zero, yeah, x equal to non-zero, sorry, when you assume that y this is equal to 0, that means y is equal to plus minus 1, this is square root of 2, and again you will get x equal to this. So the critical points that you will get, yeah, so there will be some sign difference. You need to be careful with the calculations. Mm, mm, yeah, so yeah, so this is the way to solve it. I was just giving you an hint to solve this equation. Okay, yeah, so this so our answer is that option A is correct. Just need to check it. This is the simplest question. Okay, so any question in this? Okay, so if there is no more question, we can end today's session here. Thank you for joining. Yeah, we'll see you next week. Same link. Okay.